Namaskar, I welcome all of you to my YouTube channel. This is lecture number 32 on complex analysis, and today's topic of discussion is evaluation of real definite integrals by contour integration. Students, first we will learn how to evaluate the integrals of this type, where f is the rational function of cos theta and sin theta. However, before starting this topic, I want to mention a very important point. That important point is, in order to understand this topic, you must have very good command on various methods for finding residue at poles and Cauchy's residue theorem. So therefore, I strongly recommend all of you, before watching this video, please watch my lecture number 29, 30 and 31 first. Otherwise, you won't be able to understand anything. Now, let us come back to the main topic. Students, in order to evaluate this integral, our main target has to be to convert this integral into this form. That means we have to express everything in terms of z only. Here C is the unit circle having center at z equal to 0. Next, after getting this integral, we have to evaluate this integral with the help of Cauchy's residue theorem. And according to Cauchy's residue theorem, integration along closed curve C f of z dz is equal to twice pi iota into sum of residues at the poles within the closed curve C. Students, in lecture number 31, there is a dedicated video on Cauchy's residue theorem. Please watch that lecture. Next, I am going to teach you how to convert this integral into this form in my next part. Now, let us learn how to evaluate this type of integrals. Students, to evaluate this type of integrals, we have to follow total 5 steps. In step number 1, we have to consider the contour to be a circle of radius 1 having center at z equal to 0. In step number 2, we have to write the term d theta in terms of dz and z only, and this can be done with the help of exponential form of complex number z. Students, we know that in exponential form, a complex number z can be written as r into e to the power iota theta. In our case, the radius of the circle is 1, so therefore r equal to 1. So finally, we will get z as e to the power iota theta. After differentiating and after simplifying, we will get d theta as dz divided by iota z. Next, move to step number 3. In step number 3, we have to express cos theta and sin theta in terms of z only. We know that cos theta is equal to e to the power iota theta plus e to the power minus iota theta divided by 2. In our case, e to the power iota theta is equal to z, and e to the power minus iota theta is 1 by z. So finally, we will get cos theta in terms of z as 1 by 2 z plus 1 by z. Similarly, we can show that sin theta in terms of z as 1 by twice iota into z minus 1 by z. Next, move to step number 4. In step number 4, we have to substitute the values of d theta, cos theta and sin theta here, and finally we will get an integral in terms of z only, and then move to step number 5. So after getting this integral, we have to evaluate this integral by using Cauchy's residue theorem, which is integration along closed curve C f of z dz is equal to twice pi iota into sum of residues at the poles within the closed curve C. Okay? Next, let us solve some numerical problems to understand the theory part. Problem number 1. According to problem number 1, we have to evaluate the integral I is equal to integration 0 to 2 pi 1 divided by 5 plus 4 cos theta into d theta. Now, let me solve problem number 1. So, given I is equal to integration 0 to 2 pi 1 divided by 5 plus 4 cos theta into d theta. Now, let us substitute the values of d theta and cos theta here. Students, in my last section, I had already mentioned you that d theta is equal to dz divided by iota z and cos theta is equal to 1 by 2 into z plus 1 by z, and C is the unit circle having center at z equal to 0. So, after substituting we will get integration along closed curve C 1 divided by 5 plus 4 into cos theta. Cos theta value is 1 by 2 into z plus 1 by z, bracket close, and d theta is equal to dz divided by iota z. Now, let us simplify this denominator first. So, finally, we will get 1 by iota into integration along curve C 1 divided by 5 plus 4 by 2 means 2, 2 into z means twice z, plus 2 into 1 by z means 2 by z, into dz divided by z. So, finally, we will get I is equal to 1 by iota into integration along curve C 1 into dz means dz divided by z into twice z plus 5 plus 2 by z. Next, let us multiply both numerator and denominator by the term iota. So, finally, we will get integration along curve C minus iota into dz divided by twice z square plus 5z plus 2, and this denominator can be written as minus I dz divided by twice z plus 1 into z plus 2. Here we have seen that we get an integral in terms of z only. So, therefore, this integral can be written as integration along curve C f of z into dz, where f of z is equal to minus iota divided by twice z plus 1 into z plus 2. So, we have seen that f of z is equal to minus iota divided by twice z plus 1 into z plus 2. Next, our target is to find out the poles. We know that poles can be obtained by putting the denominator equal to 0. First, let me write these points. The poles can be obtained by putting the denominator equal to 0, that is twice z plus 1 into z plus 2 is equal to 0. So, from this we have seen that z equal to minus half and z equal to minus 2 are the simple poles, and the location of these poles are at this point and at this point. Again, we have seen that out of these two poles, only the pole at z equal to minus half lies inside the given circle modulus of z equal to 1. So, let me write these points. However, the pole at z equal to minus half lies inside the given circle modulus of z is equal to 1. Now, let us find out the residue at the pole z equal to minus half. So, therefore, residue at z equal to minus half is given by limit z tends to minus half z plus half into f of z. Here f of z is minus iota divided by twice z plus 1 into z plus 2 bracket close. Next, let us take common 2 from the denominator of this term. So, finally, we will get 1 by 2 limit z tends to minus half z plus half and z plus half will be cancelled out. So, finally, we will get minus iota divided by z plus 2. Next, let us put the limit. So, after putting the limit, we will get 1 by 2 into minus iota divided by minus half plus 2. After simplifying this term, we will get 1 by 2 into minus twice iota divided by 3. So, finally, after simplifying this term, we will get residue at z equal to minus half as minus iota by 3. Finally, let us apply Cauchy's residue theorem to evaluate the integral. So, by Cauchy's residue theorem, we have I is equal to twice pi iota into residue at z equal to minus half. We have seen that residue at z equal to minus half is minus iota by 3. Let us substitute here. So, finally, we will get twice pi iota into minus iota divided by 3. So, after simplifying, we will get the value of the integral as twice pi divided by 3. So, this is the answer. So, this is all about today's video, and I hope that you have learnt a lot from this video.